Welcome to part 5 of this week's online lecture. In part 5 we will continue our discussion of analysis by infrared techniques. So let's compare the skeletal and group vibrations. What are they good for? Well, for the skeletal vibrations, because of the manner in which the bends and stretches couple together, they are highly specific to the type of molecule. They occur in a range somewhere between 700 and 1400 wave numbers. And this part of the infrared spectrum is what is known as the fingerprint region. The structure in the fingerprint region can be used to unambiguously identify the molecule itself. I'll give an example of that in just a second. Group vibrations, however, occur at characteristic ranges of frequencies according to the particular group. They don't change greatly when incorporated into different molecules. The carbonyl stretch always occurs at roughly the same frequency. The OH stretch occurs at roughly the same frequency. It doesn't matter what the rest of the molecule is, as it is largely decoupled from the rest of the molecule because of the differences in frequency. So this is a good way with which we can scan molecules for particular functional groups. However, if it is in the fingerprint region, it may not be of much use. But if it is above 1400 wave numbers, then it can really be quite useful. So these are the stretching bands that we might see. We have the OH, CH and NH stretches occurring at very large frequencies because they have small reduced masses. Then we've got the triple bonds again occurring at much high frequencies, around 2500 wave numbers or so. We then have double bonds occurring at frequencies between, say, 1500 and 2000 wave numbers or so. And then we've got the bending mode vibrations associated with NH, CH and OH, which are still at pretty high frequencies. And then the bends and perhaps the halogens occurring at even lower frequencies. It all makes sense with what you would expect according to the force constant and according to their reduced masses. If it is a very large molecule and the group frequency is occurring below 1400 wave numbers, then these can get lost in the fingerprint region. But if it is a relatively small molecule, then the low frequency vibrations can still be quite useful to identify functional groups. Now, I don't expect you to memorize any of these frequencies. This table here is purely for reference purposes. Let's have a look at 2-propanone and 2-propanol. What can we see here? Well, propanone, being a ketone, has a carbonyl group present, and you can see its characteristic frequency here at around 1700 wave numbers or so. What about propanol? For propanol, we expect to see OH stretches at high frequencies, but we also have a CO stretch occurring at around 1000 to 1200 wave numbers. A nice broad CO stretch is going on here. So stretches kind of make sense. But in organic molecules, the carbon atom is in a tetrahedral geometry bonded to 4 atoms. So there are other ways of describing group vibrations rather than just being stretches or bends. Say we have a system where our carbon atom is bonded to 2 atoms which are free, and the carbon atom is bonded to the rest of the molecule. Then we might have a symmetric stretch where the 2 bonds are stretching in phase with one another. But of course we can also have the analog where the 2 bonds are stretching out of phase with one another, and this leads to the asymmetric stretch. We can get an in-plane rocking motion like this. These are just traditional ways of describing such motions. We can also get an in-plane scissoring motion. And of course we can get these sort of out-of-plane twisting motion. And then of course we can have an out-of-plane wagging motion. Again, I don't expect you to memorize these. These are purely for reference purposes. If you need to describe these things in your experimental work, then this is normally the way we do so. The symmetric stretch and the asymmetric stretch will be occurring at higher frequencies, The asymmetric stretch is normally at a higher frequency than the symmetric stretch. The rocking motion and scissoring motion will be at slightly lower frequencies, but those are generally at higher frequencies than the twisting and wagging motions, the wagging motion being the lowest frequency vibration. Here are a few other motions that we have a name for in specific types of molecules. For a benzene molecule, for instance, we can get a breathing mode where the whole molecule seems to be breathing in and out. Not only in the benzene molecule, but anything else where the molecule seems to be getting larger and smaller in proportion with everything else. Such a vibration is called a breathing mode. And for a molecule like ammonia, you can also have an inversion mode, where the molecule looks like it's trying to invert, like an umbrella being blown open. Well, this is the end of part 5 of this week's online lecture. Please continue on to part 6.